Let's talk about analysis of variance, ANOVA. We know how to test whether two means are the same. We use a t-test. To test whether three or more means are the same, we use analysis of variance, ANOVA. Are larger cars safer? Here are chest deceleration measurements from crash test dummies. These are the small cars, these are the medium, these are the large. The deceleration is measured in g, where g is the force of gravity. So the higher the value, the more likely there will be an injury. The cars and the tests were from around 2007, so some of these brands like Saturn and Pontiac don't even exist anymore. Find null and alternative hypotheses. The null hypothesis, as always, means no difference. It's going to have an equal sign. mu1 equals mu2 equals mu3. The alternative hypothesis is that there is a difference. Not all of the means are the same. So the null hypothesis is that all of these cars are equally safe. In other words, the small, the medium, the large, they're equally safe. A more formal way to put this would be let y1 equal the chest deceleration measurements from small cars, y2 from medium, and y3 from large. The null hypothesis is that the mean of the small equals the mean of the median equals the mean of the large. The alternative hypothesis is that not all of these means are equal. Now be careful. The alternative hypothesis is not that all of the means are different. Because, for example, if mu1 equals mu2, but those two don't equal mu3, we would still reject the null hypothesis. And we would accept that not all of the means are equal. We want to do a hypothesis test to compare the means of these three independent groups. Do the data satisfy the required conditions? So here's what we've got. We've got nearly normal. The population for each treatment group seems nearly normal. ANOVA works well unless the population is far from normal. Similar variances. Populations have similar variances. George Box, the statistician, showed that if the sample sizes are similar, ANOVA works well even if the largest variance is less than 9 times, even as long as the largest variance is less than 9 times the smallest. That's a big difference in variances, so they don't have to be exactly the same. Random. Data collected sufficiently randomly. Independence. Groups are independent of each other, not matched or associated, and the data within each group, those are independent of each other. One factor. Data are categorized according to one factor. This is a one-way ANOVA test. Here's what I mean by that. In this case, our data are categorized according to size of car. If we also categorize them according to whether they're convertibles or not, that would be a two-way ANOVA test. In other words, if we further subdivided each of those 3 categories into 2 categories. We're not going to do that, though. Okay, these are okay normal probability plots, or QQ plots. They more or less follow straight lines. These normal probability plots indicate that the population is approximately normally distributed. These normal probability plots are not okay. They indicate that the population is not approximately normally distributed. This one follows a definite curve. This one's an S-curve. Those are red flags. These are what our normal probability plots look like. So they're okay. They don't follow the line exactly, but that's because they're so small. So they're adequate. And the variances of the treatment groups are roughly equal. Okay, so we've got populations that are nearly normal. The variances are similar enough. Yes, the data were collected, the cars were collected randomly. We've got independence, and it's only a one-factor ANOVA. Okay, so we calculate the test statistic F. We save the best for last, one of the hairiest formulas we'll see. Okay, it's a summation n sub I. N sub I is the size of sample I. X sub I, that's the mean of sample I. X bar, X sub I bar, I should say, is the mean of sample I. X bar is just the mean of all the values in all the samples. So that numerator is divided by k minus 1. And then we've got n sub I minus 1 times the sample variance, sample I, over n minus k. N is the number of total size of all the samples, summation n sub I, and k is just the number of samples, number of groups. Okay, so this stuff here is the sum of squares for treatments. This stuff here is the sum of squares for error. And then we divide by k minus 1 and minus k. And we get the mean of squares for treatments and the mean of squares for error. So what does this all mean? Pardon the pun. The numerator is the variation between samples, and the denominator is the variation within samples. Now, our rejection region is f is greater than f star. we would reject if f is too big, because that means there is more variation between samples than within samples. Again, if f is big, that means variation between samples, like between 1 and 2 and 3, is pretty big compared to the variation within samples. And again, we would reject in that circumstance, because that's an indication that the underlying means are not similar at all. One way to do an ANOVA test is to use the hypothesis testing feature on the graphing calculator. Oh, hallelujah. So we're really not going to be using this formula too much. Using the graphing calculator, determine whether we should reject or fail to reject the null hypothesis. Okay, so what you do is you press Stat and then Edit and then enter the observed data and list L1, L2, L3 like we've done before. Then you press Stat, Tests, ANOVA. If the lists are in L1, L2, and L3, you just enter ANOVA, L1, L2, L3. And here's what you end up with. F, for example, is 4.09. The p-value is 0.028. Oh, we know what that means. And for the factor, that is the treatment of the numerator, we know the degrees of freedom. Okay, so both the numerator and the denominator have degrees of freedom. We also know the sum of squares, and we know the mean square for the numerator as well as for the denominator. We know those. Okay, let me show you what those mean. Now recall, the degrees of, in this case, the degrees of freedom is this number, k minus 1. That's the degrees of freedom for the numerator. That's the degrees of freedom for the denominator. The calculator also told us the sum of squares for treatment and error, and also told us mean of squares for treatment and for error. Okay, f equals 4.09, which has a p-value of 0.028. Oh, we know what that means, so we reject the null hypothesis. We conclude that not all of these means are equal. Now, what if the only thing I told you was that the sum of squares for treatments is 162.87 and the sum of squares for error is 537? Could you test the hypothesis? Yes, actually you could. So again, k is the number of samples, n is the total size of all the samples. You just plug in what we know. So you don't really need this formula here. It's correct, but we don't need it. You plug in SST equals 162.87. SSE is 537. K in this case is the number of samples minus 1, so that's going to be 3 minus 1 because we have 3 groups, minus 1. And then n, that's the total size of all the samples. So the denominator is going to be n minus k. We have a total of 30 cars minus the k groups. Okay, plug in all those numbers, we end up with this. That's our mean square for treatment, mean square for error, 4.096. That's what we got earlier. The rejection region is f is greater than f star. F is 4.096. We find f star, that critical value of f, by entering f table in a search engine. And we're going to end up with something like this. So notice we have degrees of freedom for the numerator and degrees of freedom for the denominator. Okay, so we had, let's see, just recall that the number of degrees of freedom when we do that, we're going to end up with a table like this, an F table. And it's categorized according to degrees of freedom for numerator and degrees of freedom for denominator. So the denominator in this case, the degrees of freedom, as we pointed out earlier, was n minus k. That's 30 minus 3, which is 27 in other words. Okay, so this is the row we're going to look at here, the 27 row. The numerator has 2 degrees of freedom. Denominator has okay, and we end up with an F table that looks like this. The F table is categorized according to degrees of freedom for the numerator and degrees of freedom for the denominator. Okay, for the denominator, we saw we had n minus k, which is 30 minus 3, in other words, 27 degrees of freedom, so this is what we want here. As for the numerator, we saw earlier that was 2 degrees of freedom, 3 minus 1, in other words, 2. We saw that earlier. And if you don't believe me, this is where we saw that. Okay, this k minus 1, that's our degrees of freedom for the numerator, n minus k, degrees of freedom for the denominator. Okay, So 2 degrees of freedom for the numerator, 27 degrees of freedom for the denominator. Let's see, so it looks like 3.35 is where we're at. Okay, our critical F value, F star, is 3.35. So our rejection region is F is greater than F star. F is 4.096, which is greater than F star, 3.35. So we reject the null hypothesis. Based on the data, which cars seem to be safest? Which cars seem to be least safe? Here are the means of the cars in each category. For the small, chest deceleration average 44.7, 42.1 for the medium, 39 for the large. So the large cars appear to be the safest, and the small cars appear to be the least safe. We could use the Bonferroni method to figure out which of these contributed most to the rejection, but that's beyond the scope of the course. We're not going to talk about that. Suppose that our decision turns out to be incorrect. Have we made a type 1 or a type 2 error? Well, we reject the null hypothesis. If this is incorrect, that means we shouldn't have rejected the null hypothesis. We should have failed to reject the null hypothesis. If the null hypothesis is true and we reject it, we have committed a type 1 error. By the way, talk about safe cars. This is the biggest car in the world. It's called, crassly, the American Dream. It's got 26 wheels, a king-sized waterbed, a swimming pool with a diving board, a jacuzzi tub, a helipad. You might not have noticed that, but there's a helicopter that's landed on the back of the car. And it's 30.5 meters long. That's like 6 minivans.